Good afternoon, all. Again, after the tea break, see some instructions for the past participants. So, can I give?
Yes, sir.
Yes, ma'am. Yes, ma'am.
Okay, fine, fine. So, all the participants have to take help of YouTube videos for material which you require for tomorrow's online quiz. Okay, which will help you in tomorrow's online quiz because many of the participants are asking me where is the material for the test. So again, I'm repeating the YouTube link which is given in the instruction, but I'll be sharing in the chat box again. Okay, please refer it. Again, if you have any questions or queries, you can type it in a chat box. Regarding the feedback, again, once again, feedback will be only once for the issuing of the certificate. So tomorrow you have to log into ATAL portal where from where you have registered. So log into the ATAL portal and there only you have to give the feedback for the issue of the certificate. And please remember it is a compulsory task giving the feedback on the ATAL portal. Okay. So you have to, it is mandatory for the issuing of the certificate and the certificate will be issued to you from directly ATAL Academy. Okay. And regarding the yesterday's Google form which was shared for feedback, it was not a compulsory or not a mandatory task, but we'll be waiting for your selfie and videos, either selfie or video, or you can share both with us. But again, it is not a mandatory task. I think these things are clear with participants.
Madam, please also tell them about the structure of the quiz, timing and structure.
Okay, okay. So tomorrow's online quiz will be at 3:15 to 4:15. It will be of 1 hour. There will be 30 questions, 2 marks per question. Okay, so it will be total 60 marks questions, 1 hour, and it will be of MCQ type. Okay.
So, as Madam said, the quiz will be of multiple choice questions type. There will be four options. Out of that, only one will be correct. It will be floated by Google form. The link will be shared in the chat box here itself. So you have to just copy it and open it in your browser. It will be a Google form and you have to attempt the quiz. Remember, appearing for this quiz which is there tomorrow and getting 60% marks in that and 80% attendance and giving feedback on ATAL portal. These are the three compulsory that tasks that you have to do, okay, to get the certificate. Okay, please carry on.
Now I request Prasid sir to resume the session again. And sir, one participant has asked, can you increase the font size?
Yeah, I did that. I think it is
Okay,
okay
sir.
now.
Thank you.
I raised a little bit. Okay. Uh, so let us resume. Um, okay. So we started with a single uh, link manipulator. We introduced the concept of kinematics, universe kinematics, and the workspace of the robot. And we also saw a script which can plot the workspace of the robot, so we can see whether our working region comes under the workspace of the robot or not. And then we also looked at the, the problem of singular points where the Jacobian matrix of the kinematics become singular. This Jacobian matrix is the matrix which gives us the relation between velocities. The j theta is in fact the partial derivative with respect to j theta use this kind of matrix. This is J theta matrix, Jacobian matrix, and the singularity of Jacobian matrix is also to be investigated. We have to see where are the points in our workspace which gives us singular Jacobian matrix, so that uh, at those points we have a loss of movement. At those points we have a restriction that we may not be able to move in certain uh, direction. Right? So we may not able to move the end effector in certain direction. So those are the singular points, and uh, voice is not clear. Is it? There volume increase. Okay, I have increased the volume a little bit. Uh, yeah. Okay. So as I was talking about the singular points in the Jacobian, that gives us that in the geometry of our robotic manipulator, there are some points from where we cannot move in certain directions. Right? So uh, it is good to know the restrictions that our robot poses. Then we saw the singular points for our tooling manipulator. And at theta is equal to 0, we cannot move in x direction. So that is one of the singular points where we use the direction in which we can move the end effector. Then, uh, yeah. So then we built this robot in MATLAB using this MATLAB robotic toolbox uh, command. First, first command we used was the rigid body tree. Using this command, we created a rigid body robot. Then we kept on adding the bodies and joints in that robot. And finally, we created our robot, which we had seen using the command show robot. So now here our tooling manipulator robot uh, is ready. Now, what do we want to do? What do we want to manipulate with this robot? Is uh, let us give some path in XY plane, and let us try to move this end effector on that path. And what path do we want to select? Let us uh, select this circle. And so we'll put this circle XY coordinates in an array, and then we will try to solve this inverse kinematics problem. So now this is an inverse kinematics problem, uh, which is hard and which is uh, uh, not almost not solvable by hand. You can see here the inverse kinematics problem that we had put up one equation that theta 2 is equal to this x square plus y square minus L1 squared minus L2 squared divided by 2 L1 L2. So for each x and y, we have to compute this theta 2, and that 2 it will have two values plus or minus, and then there is also such equation for theta 1. So this inverse kinematic problem has to be solved, and also it has to be the singular points have to be taken care of. Okay? So by hand it is almost impossible task, but MATLAB has commands to solve this inverse kinematic problem. So we will move ahead. So first we will have to create this circle in MATLAB, and we should check also that the path we have decided for the robot whether that path is coming under the workspace or not, right? So let me create first circle with a radius of 0.15 meter, and we'll put a constraint that this is required in uh, column vector. So count is equal to length of t, and we'll center our circle at 0.3, 0.1, and we'll put z coordinate 0, and the radius will be 0.15. Then to create the points, we vary the theta over this time. We have 2 pi, we divided 2 pi into, uh, so we took the last element of time. So we divided the entire circle 360 degrees into within that time, and then this multiplied by t creates the each theta point, each angle, and then we have the point of the circle as center plus the radius multiplied by, we will have cos, we defined theta earlier, cos theta sin theta, and then we have the last one. Yes, we, okay. So these are the points of the circle are created, and we can execute E. mm, E. Okay. So now, so these points we can check with our workspace whether these points which we have uh, made this circle is within our workspace or not. So this was the script where we created our workspace. So let me execute this script to show the workspace first. So this was our workspace for our robotic link manipulator. The workspace is in the XY plane, the angular region in XY plane. Right? Now, whether this circle falls within this workspace, let us check, and let us put this circle points in this script, and let's see what happens. After search, we'll hold on to the graph, and then calculate the circle points, and then we plot these points. Okay. Now, if we run this script again, we will see the circle that we defined along with the workspace, right? So now that is our workspace, because workspace is z coordinate we had kept as 1. So uh, it has this offset of on z axis of 1 unit, and the circle we have plotted as at z0. You can see here, these are the zeros. We have kept the z coordinate, the center z coordinate is 0. So, then uh, so now we can see here, if we go to the xy plane, we can see here that the circle is entirely covered by the workspace. So that means that our workspace covers this circle of points where we end effector to move. So end effector can follow this path because they fall within the workspace. If I do this, for example, instead of center being at point 3, point 1, if I keep the center at 0.6 and let's say 0.3, right? And then let us see that plot again. Now, uh, let us check this circle whether it falls. Yeah. Now you see that the circle falls outside the, the workspace of this mobile robot. So if this tooling manipulator has the workspace of this angular region, but the circle that we want the end effector to follow, it goes outside the region where uh, the end effector can reach. So this problem solution will fail. If you plot, although we have not yet seen how to solve this problem, how to solve this inverse kinematic problem in MATLAB, but even if we try to solve it, it will fail. Solution will fail because the solution does not exist. Okay, so this must be taken care always. So anytime when you are working with this robotic manipulators and your programs are failing, your coding is failing, then one must see whether what you are trying to achieve with the robot is achievable or not. So it should be in the workspace region. Okay. So the initial circle that we made is within the workspace that we have verified. Now we move to solve the kinematics, inverse kinematic problem. Right? So to solve the inverse kinematic problem, first we need to define the home configuration. So where the robot is initially. So from which location we want the robot to start moving. We want the robot to start moving from a point Q0, which will be coming from the home command called home configuration. Okay. And here we have a variable called end that is length of Q0, that is degrees of freedom. Although I have not talked about degrees of freedom, but I believe many of the participants are aware of the concept of degrees of freedom. So this is two dog manipulator. So this two links manipulator is two dog because we have 2 degrees of freedom. We are varying these two variables independently. Both of these variables can be changed independently. They can vary independently of each other. So we have 2 degrees of freedom here. So end of variable here will be 2. So this home configuration command gives us the initial configuration of uh, the robot object that we have created. So let us check what is the home configuration. Home configuration should be both theta 1 and theta 2 0 because if you remember when we uh, saw this robot when I showed this robot, this is the home configuration. Is home configuration where both the theta 1 and theta 2 are 0. Right? So, so Q0 should be a vector of two elements 0 0. So let us see that whether it is to home configuration of robot is 0 0. Correct? So robot is at rest and it is at home configuration. We have taken home configuration in a vector called Q0. We have uh, also brought out the degrees of freedom from Q0 and then yeah. Then we are now I think ready for solving the inverse kinematic problem. So the command for inverse kinematic problem is inverse kinematic. In where inverse kinematic for this rigid body tree problem. So MATLAB has inbuilt algorithms to solve this inverse kinematic problem. So we will solve this inverse kinematic problem and we will uh, put our answer in a variable called IK. Uh, yeah. So this is not yet complete solution. We here some weights also. What is the use of these weights? So, let me explain when we move to the next part of the solution. Okay. And effector we specify in the body. And effector, what is the name of the end effector? We have kept the body, which is end effector. The name of that body we have kept as tool. If we see here the last body, the fixed body that we had created is called tool. Right? So that is our end effector. Right? So we have end effector. We created this IK object, that is the inverse kinematics object, and these weights. I will explain when the weights is used. And now we have to solve this inverse kinematic problem for all the points on the circle. Right? So now we have to give all the points of the circle to this IK, and we have to receive the theta, the theta angle. That will be the solution for our inverse kinematic problem. Right? So for each x and y on the circle, what is the value of theta 1 and theta 2? Correct? That is our solution. So now for that we will need, of course, we will need a loop, and the loop that we will make is the for loop. Initial, we already have Q0, so no need to define another initial. So we will use that Q0 for initial condition. So for I is equal to 1 to count, and then point is equal to first point. So we took the first point from our array of points, then we pass that point to the IK solver, inverse kinematic solver, and in the inverse kinematic solver, we are giving this uh, arguments, this end effector. So we have to tell which body in our robotic manipulator is the end effector. So these XY coordinates are of which body? So these XY coordinates are of the end effector. End effector is our tool. So in our robot frame that we created, our robot frame, the tool is the end effector, and then the the points that we which are following are the points of the tool, right? That was created in the rigid body tree. And again, we have to create this transformation from translation vector to T form that is required by this command. So this IK command requires us to apply the transform for the translation, and then these are the weights, and then Q0. Okay. So now let us see all the components of this IK. This end effector we saw. Then this is the transformation for the point that where we want to reach. So we want the solution for, this is the point XY location. We took the first point from the points array. Points is an array of 103 by uh, uh, 3 columns and 103 rows. Right? So the third column is the Z, which is 0. If we see these points array, so the Z coordinate is 0, and we have this X and Y coordinates. These X and Y coordinates we plotted, and we checked that these X and Y coordinates are for the circle. Right? So we uh, took one point from this array, and then we supplied the transformation matrix for that point, and then we need these weights. These weights are uh, considered from 6 degrees of freedom. So this IK can solve the 6 DOF problem. Our problem is only 2 degrees of freedom, right? So these weights are to be given that which degrees of freedom are we going to solve. Solve for. Right? So these weights, first 3 degrees of freedom are rotational degrees, roll, pitch, and yaw, which we are not doing anything about. We have considered a planar robot which is moving only in x and y, and then z is also 0. Right. So for the weights vector which is required by the IK solver, right? So this IK solver requires the weight vector in this format. We first give the rotational degrees of freedom for which you want to solve for, and then with translational degrees of freedom x, y, and z. Okay, so this is explained in the help of IK. If you see the help of IK, okay, help of inverse kinematics. Yeah. So here weight, uh, the weight on each component of desired force is the vector base. Right? So our desired force contains only x and y. So we are weighting them as one and one, and then we are not weighting, we are not giving weight to uh, any other degrees of freedom. So this weights is required for this solver because also the solution is not unique. So it needs to know that uh, which coordinate, which degrees of freedom you are more interested in. We are more interested. Right now, we are more interested in both the coordinates equally. Right? We are interested in x and y both equally. Right? Uh, so it will optimize the trajectory of this inverse kinematic problem according to those coordinates. So it will give more weightage to those coordinates which we have provided in the weights vector. Right. While solving, it will yeah. And then the initial Q0. Okay. So uh, yeah. Okay. So that is here we will need to specify one Q initial because every time this Q initial will change. So Q initial is equal to Q0 is required, right? And then after getting this Q solve, we will put this in the vector Qs. So this is our first solution. Let's say I is equal to 1. We are starting. So the first theta we have solved for. I come here as Q solve, and then we will change our Q initial is equal to Q solve. And then here also we need to change it to Q initial. Okay. So now we started from the Q0. We took the first point from the circle. We solved the inverse kinematic problem with that Q0. That Q solve solution. Q solve solution will contain two angles, right? So that is our the solution of our inverse kinematic problem. The two angles we received by the solution of inverse kinematic problem. Then this Q solve is stored in the solution array as the first element. Then second element we will populate this array as we solve for all the points, and then we change the Q initial to Q solve. So now for the next point, the initial point is the point for which we previously solved for. Right. So now that is complete solution. Now you see that MATLAB took some time to solve this problem, and then it has come up with the entire solution. So this is the complete solution of the problem. So this theta 1 and theta 2 array, this is the QS vector which is created, which we created in the for loop, and this is the entire vector of all the angles that are required to uh, to traverse the trajectory around this uh, circle. Right. So now, if we move theta one and theta two according to these values, then it is said that the end effector will move on the given circle. Okay. So now let us test that whether that is happening or not, whether it is correct solution or not. So we will plot uh, for each q value. So now for that we will actually in fact solve the kinematics problem, forward kinematics problem, and we will animate that entire trajectory so that we will see uh, the end effector rotating on a circle. Okay. So then we open a new figure. In the figure we show the robot at US first solution. So the robot and the angles will be to the first point in the solution, and this requires a column vector. So we will make it transpose. Okay, and then use this. Let us just see this view. Okay, now can you see that the robot has moved later has moved according to the q0. Okay, so this is our 0 0 point, right, in xy plane. This is it. According to the initial value that we had given, it has moved to the Q0. Okay. Now, now from this point onwards, so this is our 0 0 point xy 0 0, and the manipulator has moved. So theta one is some negative some value. Here we can do theta one is negative and theta two is positive some value. We can also compare it with the QS solution. So QS solution is to that first theta 1 is minus 0.4 and theta 2 is 1.7. So that is visible here. So now this is x axis, y axis. Our origin is x here, and theta 1 is negative some value and theta 2 is positive some value. This end effector is at the circle that we want to trace. Okay. So this is the first point that we have plotted, and we have seen that it is correct. Okay. Now we have to loop this uh, entire entire procedure in a for loop. So we'll put some properties on the axis to get the axis and axis reaction, because we just want to see the xy plane. I was rotating in 3D, but then we can set the axis property by using this command also. We fix the axis as orthographic axis on this figure. We also plot the circle, so we see that whether uh, the end effector is moving on the circle that we have defined or not. We plot circle and we restrict the axis to, okay, so that is the setup of the figure. Now we set up the animation for the animation to show that end effector moving around this circle. Uh, we need to put this in the for loop. We'll take 15 frames per second. So frames per second we define as 15 r is equal to the rate control command gets this value of 15 frames per second, and then for loop until all the points on circle are exhausted. And then count, we keep showing the robot moving on one point after another point. Take the first point, draw now, and then wait for R. That is the rate control. And then now we should see, if we execute this script, we should see the animation. I think I set up the axis incorrectly. Let me see the value. Yeah. So I think here it should be minus. So I believe everyone can see this end effector moving in a circle, but the circle is somehow not plotted. We check why. Uh, we want to plot the circle also, and on the circle we want this end effector to be shown as moving. So the issue here instead of point, I have put point. Okay. So now we will see that circle also and the end effector moving on the circle. Okay. So we have created this circle. So this is the path we want our tooling manipulator to move on. And then this is the inverse kinematic problem, considerably harder problem. Then we solve this uh, problem using MATLAB's robotic toolbox commands, that we define this circle XY point, and then we, uh, we solve that inverse kinematic problem to give us theta 1 and theta 2 angles, uh, such that this end effector will move on the described circle. Okay, so that is the end of, I think, this example. This example is, I believe, understood very well. And if there are any questions on this example, we can see, uh, or we will move to the next last part of this session. Last part of this session consists of uh, dynamics. So after understanding the kinematics, inverse kinematics, uh, workspace, Jacobian, almost all the concepts we have covered by using this small example, and we also saw how to uh, create a robot geometry in MATLAB. One important related before we move to the dynamics, related concept is of this URDF model. So you might have been introduced to URDF model on the day one by uh, Ajit, that URDF format for the robots is uh, is used in ROS, and many manipulators nowadays are running ROS. Right? So if you have some industrial manipulators, manufacturing business, so those who are making robotic manipulators for industrial automation. So for those robotic manipulators, may be running ROS. Right? So it gives good flexibility in programming the robotic manipulators for different applications. So if you are going to work with ROS, then you have to work with URDF models also. Correct? So now MATLAB has also facility to import URDF models. So this is the one way. This was the MATLAB way of creating the model. Right? So this was the MATLAB way, the rigid body tree robotic manipulator we can create in MATLAB. But MATLAB gives us facility to uh, import URDF models also. For example, we have a URDF model of tooling manipulator. So let me bring the URDF model. Mm, I think let me create one. Okay, so let me increase the font. Yeah. So to know that here URDF model, URDF format for describing what is an XML format. So you have to first write the XML interpreter directive, that the code that is going to follow is in XML. So that XML directive is written, and then we create a robot tag, and this completes the robot tag. The name of the robot we will give the name tooling, tooling planner something. Yeah. So then we will create another link. That name is base underscore link. And let me show also save this. for syntax highlighting, I wanted to say that, yeah. So now we are saying that there are several links here. There are four links. There is one base link, then there will be link 1, link 2, and then end effective. Right? So now let us, we have created, copy pasted, I created four link directives and then link tags, and then I am renaming each link. Okay, that's all the links are created. Next up is to create joints. So in this URDF format, we have joint name is the first joint one. It is continuous joint. Okay, and we'll finish this joint tag, and then uh, parent of the joint is link is equal to child. We have to specify for each joint and axis we have to specify. This make it zero. So, so we copy this joint, make two more joints just like we created in MATLAB. And the second joint is Q2, it's continuous, but now the parent is with link 1, child is link 2, and now we need to specify origin also here. And axis is 0, 0, 0. So, and then in the third joint, we name it as again, suppose it's 6, or we can just say it is not a joint. It is not a joint, it is fixed. Parent of this and effector is linked to, and child is nothing. There is no child, it is at the end. Okay, and this will be 0.3. Okay, so the same uh, tuning manipulator we have created in URDF format. For this, you have to learn URDF format and each tag. Right? So this parent tag, this child tag, origin tag. I have just written all these tags because it has introduced this URDF format and all these tags. I think that we have taken in quite good detail this URDF format, right? So this URDF format I created my uh, robot, and let us try to import this URDF into MATLAB and see how it looks. Now, let me clear the workspace. And now, uh, your dear test, we are just testing how it works. The command is import robot, and from the current directory. Yeah, so in current directory, this is the tool link to underscore link dot urdf file that we have created. We will import it as a robot. We say uh, tool underscore link dot urdf. Mm, there is some error. We need to look at this error. Open this file in editor and check. Someone to robot name. Hmm. The error which shows here is the axis must be terminated by the matching and attached slash action. Right? So you have not ended the axis. I need to do that. Okay. So yeah, so that slash here. Okay, slash. And this has also end. So now let us import. Try to import again if there are some errors. We see another error. The XYZ attribute of robot tool is Q1 element is invalid. Tooling body Q1. Also, I think here we have the origin. Huh. So now all the errors are corrected and the URDF model is imported. Now this URDF test is also, you can see the variable type is rigid body tree model. So we created the URDF model of rigid body manipulator. So URDF format on Monday just created a wheeled mobile robot using URDF, right? We have created a robotic manipulator in URDF and we have imported in MATLAB. And if you want to see this robot. So just like earlier robots, we were looking at those robots using show command. We can see look at this robot also URDF underscore test, and it will show that. So it looks similar. So we have created the same robot, so it is similar, right? So it starts at 0, 0, and then there are two links. So this is your XY plane and 0, 0 origin. Then there are two links, both of 0.3 meter length. Right? So this way we can import URDF models if we have already studied the URDF format and you know how to write in URDF format, then you can use this facility to import URDF model to MATLAB, and then you solve all the kinematics, more kinematics problem in the Um, and in this XML, you can do a little bit more also in the way that you can put the colors and you can flesh out the links properly. For example, I have this same URDF model uh, with different visual field. So let me put it here and you let me import that model. So instead of tooling or code visual or URDF, and then show you. So now you can see both the links have different colors. One is red and green, and then any factor is also shown as a cylinder. Okay, so you can do this with them. So now you have this rigid tree, rigid body tree model, and again, if you solve this inverse kinematic problem with the animation, it looks a little bit better. So you can do this. So this is again, this was the URDF model. I will not get that URDF in detail and just show that we have created a material tag which is a URDF tag, and then material name red, and its color we have created green its color, and then we have used this material in the while creating these links in this URDF. Right? So you can do good stuff when you combine this ROS URDF and MATLAB robotics toolbox also. Okay, so I think that is good enough introduction for the manipulators, robotic manipulators. The last topic that I wanted to talk about for the 15 minutes is about dynamics. So that will complete this robotic manipulation problem. So the so far what we have done is we have a robotic manipulator. We have created a robotic manipulator, tooling manipulator like this, and then we made this tooling manipulator to follow the trajectory given on inside its workspace. So it may be any trajectory which the industry may require. So this trajectory following problem is the inverse kinematic problem. We solved it. So we know the XY points. So we know the X coordinate, the position of end effector. We solved for the theta, okay, all the theta that is required along with x dot and theta dot. Right? So both of these then combined, uh, we can say this is inverse kinematic problem. Mhm. So now given x and x dot, we have taken we have said that we want to be traversed within 10 seconds. Right? So that is the velocity also. So given position of end effector and velocity of end effector, we now have the solution for theta and theta dot. So now we now know that what theta position and derivative should be for each second for the 10 seconds. So for the 10-second interval, we have taken 200 milliseconds, so zero point 0.2 with the interval of zero point 0.2 seconds at each time step. What should be the value of theta 1 and theta 2? What should be the value of theta 1 dot and theta 2 dot? That we have solved. Okay. So now the how do we so far it is okay, simulation is okay, but how do we actually produce those velocities, theta 1 and theta 2? Right? Then we have to look at the dynamics of this uh, uh, manipulator. Right? So we have so far looked at only kinematics and inverse kinematics. Now we have to look at dynamics and inverse dynamics also. Right? Because so when we want to produce this velocities and positions via some torque. We will apply some torque to this robotic manipulator. We will apply the torque. So let me write it. Want to produce this theta and theta dot, which has come from the inverse kinematic solution. Theta and theta dot by applying some torque. And torque at where do I want to apply the torque? Torque at joints. At these joints, I will apply some torque. So, but what torque should I apply now to produce this theta and theta dot? I know that this angle and this velocity is required at this particular time. But what should be the value of torque? So now I will program my motors, servo motors or stepper motors to produce this torque at that particular time. So what should be that torque? So that problem is answered by dynamics, inverse dynamics. In fact, more accurately, we can say that it is this question is answered by inverse dynamics. And what is the just like kinematics and inverse kinematics problem? Dynamics problem is dynamics problem will give you theta theta dot uh, from torque. If you are given the torque, you can compute theta and theta dot. That is the dynamics problem. So these are the state, this becomes state. So those who have already studied control systems can identify with this problem that this theta will be x1, theta 2 will be x2, and then you have this tau as the input, and you can have some state equations. And for given input, you can solve the values of x1 and x2. That is the dynamics problem. So given the torque, you solve for theta and theta dot. That is the dynamics problem. In inverse dynamics problem, you are given theta and theta dot. Theta and theta dot are given. That is the state trajectory is given, and you have to design the control. Right? So this is what in control systems, control theory, control engineers do. They are given some desired trajectory. So now we can say that this theta d and theta dot d, and then we have to design the torque. We have to design the control which will produce this this particular position at the joints and those velocities. Right? So that is dynamics and inverse dynamics problem. Now, I don't think we can go into details of dynamics, but I'll just mention what goes into this dynamics problem. So first, uh, we can derive the dynamics of these manipulators using Newton's law, also called Newton-Euler equation, which is basically the force balance. If you have studied those force balance equations, you create the force balance equation at all the points, and then you get the dynamical equation using this Newton's second law, which is equal, basically F is equal to ma, or your torque is equal to j omega, where j alpha, sorry, or I can write here omega dot. Right? So J is the inertia, this tau is the torque, and this is the angular acceleration. So using these equations, or more popular and compact way to derive this dynamical equation is, does anyone know this method? Has anyone come across how we derive the dynamic? It is called, you can put in chat box, yeah, Lagrange's equation, Lagrange's method. Lagrange method to derive the dynamic. Right? So in Lagrange method, we create something, an entity called a Lagrangian, which is in theta and theta dot. In general, if you remember the morning talk, Vrunda madam had talked about generalized coordinate. So in generalized coordinates, this Lagrangian may also be mentioned as q dot. Okay. For our problem, this Lagrangian will be in theta dot. And what is the Lagrangian? Lagrangian is kinetic energy minus potential energy. Kinetic energy minus potential energy, denoted as T minus U. L is equal to T minus U. So after finding out this Lagrangian, so, so you can see this kinetic energy is proportional to theta dot, potential energy is proportional to the position theta, and then we get this Lagrangian, and finally the dynamical equations of motion are given by this d by dt of dou L dou I. So now we have two angles. So for each angle, so let me write theta I only minus divided by theta I equal to I is equal to 1 and 2. Okay. So now you create this Lagrangian, or you form this Lagrangian, that is for your two link manipulators, we find out the kinetic energy, we find out the potential energy, then uh, so then we find out this Lagrangian, and then we differentiate the part, we find the partial derivative of Lagrangian with respect to each degrees of freedom, each theta, and we differentiate with time, subtract this partial derivative of position. I think so. I have made a mistake here. This is theta dot. This is theta dot I. This velocity, and here we have partial derivative with respect to position. And this will give us the dynamic of the robotic link manipulator, and then we can supply theta d. We can supply theta d and theta d dot into these equations, and then we can find out, we can solve for tau. So at each link, what torque is required, that we can create, and then we program our motor to produce that torque and that speed that is required. Right. So I think I will stop here. That will be the end of the session. If there are some questions, we can take the question.
Any
There is a
questions?
question I can see. Yeah, I can see one question where we will get help for writing such program in MATLAB from scratch. Yeah, so the help is available in MATLAB itself. I'll show the help. For example, what I showed you, the MATLAB URDF import. So I had seen the URDF import yesterday only. So this URDF import, as an import, this is, yeah. So you see this MATLAB help itself has a URDF primer, what is URDF, and all these commands are shown here. URDF format is also shown, and finally one model is also created in URDF. So MATLAB itself has a very good help inside it, right? So this kind of model they have created in URDF. Right? So so you can refer to MATLAB's help very extensively. MATLAB itself has a good amount of help available, and MATLAB file exchange also has very good files. There is one nice yeah, uh, package which is made by MATLAB staff designing robot manipulator algorithm, which is available on MATLAB's file exchange. So here they have, I what I did was very simple, and one specific problem. They have created this libraries to solve uh, this manipulator algorithm for a very complex robots. Six block robots also you can solve using this library. So all the help is given here, and they have these videos also. So this particular, if you Google this designing robot manipulator algorithm, you will get some YouTube videos by the authors of this. So yeah, so you can get the help in MATLAB itself. Yeah. The required version for this kind of yeah, robotic program. So the version I am using is 2020A, but these the commands that I have used are available since I think almost 10 or 12 years in MATLAB. So the commands that I used, you can use in maybe one or two are updated commands. So what I did here can be done in MATLAB 2010, 12 also, but maybe a couple of commands are changed. Uh, like this fixed transform, that fixed transform command is changed, updated, etc. Some of the commands are changed. So this my program will work exactly starting from MATLAB 2018, I think. In 2018, they changed some commands or they deprecated some commands. But the task that was performed in this program, that task was being performed many years ago in MATLAB with some minor change in tweaks in command. That's all. Yeah. Okay. Any other question? I do not see in chat. Uh, okay. So
Any
there are no
questions,
questions. So we
participants?
can.
So one has written, Sridhar Khandekar sir has written that do not know about it. That we can do in MATLAB informative sessions.
Thank
So
you.
any other questions?
No.
Okay. Uh, Thank you, sir, for explaining fractional calculus in detail.
Hello.
Sorry. Sorry, I got disconnected. Okay. Thank you, sir, for explaining MATLAB program approach for robotic manipulator design in detail. And thank you once again. Dear participants, we are meeting tomorrow at 11 o'clock sharp, 11 a.m. And there will be a session from Sadhvi Karishma ji on art of living. Okay, so please do not miss all any sessions, and we'll meet at tomorrow 11 o'clock.